Out there, on the frozen fringes of our solar system, where sunlight is nothing more than a dim flicker in the endless dark, a tiny world drifts in silence, holding secrets that defy explanation. This is Makemake, a dwarf planet shrouded in mystery, a place so distant and strange that even the most advanced telescopes struggle to pierce its veil. Discovered in 2005, Makemake orbits in the Kuiper Belt, a vast ring of icy debris beyond Neptune, yet it stands apart from its neighbors. Unlike Pluto or Eris, Makemake refuses to give up its secrets easily. Its surface gleams with an otherworldly brightness. Its atmosphere, if it even has one, plays tricks on observers, and its strange, oblong shape hints at a turbulent past. Scientists are left with more questions than answers. Why does Makemake reflect light so intensely? What forces shaped its bizarre orbit? And could there be something lurking beneath its icy shell, waiting to be found? Imagine standing on its surface, where temperatures plunge to near absolute zero, where the sun is little more than a particularly bright star in an eternal night sky. The ground beneath your feet might be frozen nitrogen, methane, or even ethane materials that behave in ways we can barely comprehend under such extreme conditions. But here's the real puzzle. Makemake shouldn't be this bright. Its surface is somehow polished to a mirror-like sheen, defying expectations for a world so far from the sun. Some researchers speculate it's continually resurfaced by unknown geological processes, while others whisper about exotic ices or even hidden cryovolcanoes. Then there's the baffling case of its missing atmosphere. Early observations suggested a thin, transient layer of gases, but later studies couldn't confirm it. Where did it go? Does it come and go with the seasons, vanishing like a ghost in the cosmic wind? This is the allure of Makemake. It's a riddle wrapped in an enigma floating in the void. Every answer we think we have only leads to deeper questions, and that's why we're diving into the 25 most unexplained mysteries of this distant world today. From its peculiar lack of moons to the strange reddish patches staining its surface, each clue brings us closer to understanding or further into the unknown. So buckle up, because we're about to embark on a journey to one of the solar system's most perplexing places, where every discovery challenges what we thought we knew about the cosmos. The deeper we go, the stranger it gets, and by the end, you'll see why Makemake might just hold the key to unlocking some of the universe's greatest secrets. One of the most baffling puzzles about Makemake is the case of its vanishing atmosphere. When astronomers first studied this distant world, they detected subtle hints of a thin, transient layer of gas, likely nitrogen or methane, floating above its frozen surface. But when more advanced telescopes turned their gaze toward it, that atmosphere seemed to disappear without a trace. How could something so fundamental just vanish? The leading theory points to Makemake's extreme distance from the sun. Unlike Pluto, which maintains a tenuous but stable atmosphere thanks to occasional warmth from our star, Makemake orbits even farther out in the deep freeze of the Kuiper Belt. At those temperatures, gases that might normally stay suspended above the surface could freeze solid, collapsing back into the ice below. But there's another twist. Some researchers suspect Makemake's atmosphere might not be gone completely, just hiding. On Pluto, atmospheric pressure fluctuates dramatically as the dwarf planet moves along its elliptical orbit, with gases freezing out when it's farthest from the sun and thawing when it swings closer. Makemake could be experiencing something similar, its atmosphere vanishing and reappearing over decades-long seasonal cycles. The problem, we haven't observed it long enough to know for sure. Another possibility is even stranger. What if Makemake once had a much thicker atmosphere, but it bled away into space over billions of years? Without a large moon to help stabilize its climate or geological activity to replenish lost gases, the dwarf planet might have slowly bled dry, leaving behind only a whisper of what was once there. What makes this mystery so intriguing is how it challenges our understanding of these distant worlds. If Makemake truly has no permanent atmosphere, why does its surface appear so unusually reflective? Some ices, like fresh methane frost, can shine brightly even without an atmospheric blanket, but maintaining that sheen requires some process to keep renewing the surface. Could tiny amounts of gas still be leaking from below, creating temporary hazes before freezing back into the ground? Or does Makemake's surface chemistry work in ways we haven't yet imagined? Every time we think we've solved one piece of this puzzle, another question emerges, pulling us deeper into the unknown. For now, Makemake keeps its secrets locked in ice, waiting for the next generation of telescopes, or perhaps even a visiting spacecraft, to finally reveal the truth. If there's one thing that makes Makemake stand out even among its mysterious Kuiper Belt neighbors, it's the way it flickers like a cosmic lighthouse, brightening and dimming in ways that defy simple explanation. Astronomers first noticed these odd brightness variations shortly after its discovery, and the deeper they looked, the stranger the patterns became. Most distant icy worlds rotate with predictable consistency, their surfaces evenly scattering sunlight. But Makemake, it dances to its own rhythm. Its brightness doesn't just change, it does so unevenly, as if parts of its surface are reflecting light far more intensely than others. So what's causing these erratic shifts? One leading theory points to an irregular shape. Unlike planets smoothed by gravity into neat spheres, smaller bodies like Makemake can retain bizarre, lumpy forms. Think of a potato tumbling through space. If one side bulges outward or features jagged terrain, it could catch sunlight differently as it spins, creating those puzzling fluctuations. But here's the catch: Makemake's brightness changes don't always match up with its rotation period. That suggests something even stranger might be at work, like vast dark patches staining its otherwise gleaming surface. These could be areas where ancient impacts exposed darker material beneath the ice, or where cosmic radiation has chemically altered the frozen compounds over billions of years. Then there's the wild card, cryovolcanism. On other icy worlds like Pluto or Saturn's moon Enceladus, geysers of water and ammonia burst through the crust, resurfacing the terrain with fresh, reflective ice. Could Makemake harbor similar activity? If plumes of nitrogen or methane occasionally erupt from its interior, they might coat parts of the surface in bright frost, temporarily boosting its reflectivity before the volatile ices evaporate back into the void. The trouble is, no direct evidence of such eruptions exists yet. Without close-up observations, we're left guessing whether these brightness spikes are geological in nature or the result of some other, entirely unknown process. What makes this mystery so tantalizing is how it intertwines with others. Those dark patches, they might explain why Makemake's spectrum shows subtle reddish tints in certain areas, a sign of complex organic molecules cooked up by eons of exposure to space weather. The brightness variations could also hint at hidden topography, like towering ice cliffs or deep basins sculpted by ancient collisions. Every flicker of light holds a clue, but piecing them together feels like trying to solve a puzzle with half the pieces missing. For now, Makemake keeps its secrets, its surface shimmering with patterns we can't yet decipher, a silent enigma spinning in the dark. Among the many enigmas surrounding Makemake, few are as visually striking as the mysterious red spot, a splotch of color that stands out starkly against the dwarf planet's otherwise pale, icy surface. While most Kuiper Belt objects appear as featureless white or gray dots in telescope images, Makemake harbors this peculiar blemish, a concentrated patch of reddish material that has scientists scrambling for explanations. What could possibly create such a vivid mark in a place so cold and barren? One compelling theory points to Tholen's complex organic molecules formed when methane or other simple compounds are bombarded by cosmic radiation over millions of years. These substances, found on icy moons like Titan and Pluto, often appear reddish-brown and could easily explain the spot's coloration. If Makemake's surface ice contains traces of methane, relentless exposure to space weather could have transformed it into this dark, ruddy sludge. But here's the catch. Tholins usually spread more evenly across a world's surface, not clumped together in isolated patches. That raises the question, why is this material concentrated in one specific area? Another possibility is that the red spot marks the site of an ancient impact. If a rogue object slammed into Makemake long ago, the collision might have dredged up deeper layers of ice laced with organic material, exposing them to space and triggering chemical reactions. Alternatively, the impact could have melted subsurface reservoirs, creating a temporary slurry of water and organics that later refroze into this distinctive stain. Yet if that's the case, why don't other Kuiper Belt objects show similar scars? Makemake's red spot seems uniquely prominent, suggesting something unusual is at play. Then there's the wildest idea of all cryovolcanism. If Makemake once had, or still has, hidden reservoirs of liquid beneath its crust, occasional eruptions could have spewed a cocktail of water, ammonia, and organic compounds onto the surface. As these substances reacted with sunlight and radiation, they might have morphed into the reddish gunk we see today. It's a tantalizing thought, especially since similar processes are suspected on Pluto and Neptune's moon Triton. But without close-up observations, we're left guessing whether Makemake's geology is dynamic enough to fuel such eruptions. What makes this mystery so fascinating isn't just the spot itself, but what it represents, a tiny window into the complex chemistry of the outer solar system. If that reddish patch really is organic material, it could mean Makemake was once, or still is, a laboratory for probiotic chemistry, cooking up the building blocks of life in the deepest freeze imaginable. Every theory we have comes with its own set of questions, leaving us to wonder, is this just a curious stain, or could it be a sign of something far more profound lurking beneath the ice? For now, the red spot remains a puzzle, a single brushstroke on an otherwise blank canvas, one that hints at secrets we've only begun to unravel. Among the many oddities surrounding Makemake, its relationship with moons, or rather the startling lack of them, stands out as one of the most perplexing. When astronomers first discovered this distant world, they fully expected it to have companions, just like nearly every other known dwarf planet. Pluto boasts 5 moons, Haumea has 2, even Eris, Makemake's Kuiper Belt neighbor, has 1. But for years, no matter how hard scientists looked, Makemake appeared utterly alone in the void. This absence defied expectations, especially considering how common moons are among similarly sized objects in the outer solar system. Then in 2016, everything changed. The Hubble Space Telescope finally spotted a faint speck lurking in Makemake's shadow, a tiny moon later named MK2. At roughly 100 miles across, this dim companion is vanishingly small compared to its parent body, barely reflecting enough light to be detected. Its discovery solved one mystery but opened several more. Why is MK2 so faint? Observations reveal its surface is among the darkest ever measured in the solar system, absorbing nearly all sunlight that hits it. One theory suggests it might be covered in carbon-rich material, perhaps debris from ancient impacts that left it coated in cosmic soot. Another idea proposes that MK2 isn't a captured object at all, but a fragment of Makemake itself, a chunk blasted free during a colossal collision billions of years ago. But the bigger question remains, where are the other moons? Most dwarf planets have multiple satellites, often formed from the same impact that created their primary moons. MK2's lonely existence hints that Makemake's history might be more violent or more serene than we imagined. Perhaps the collision that produced MK2 was so cataclysmic that it vaporized any other potential moons. Or maybe Makemake's orbit through the Kuiper Belt stripped away additional companions over time, leaving only this one dark survivor. There's even a chance that other moons exist but are simply too small or too dark for current telescopes to detect. The mystery deepens when we consider MK2's bizarre orbit, a wide, irregular path that takes it nearly 1,000,000 miles away from Makemake at its farthest point. Such an extreme distance is unusual for a moon so small, raising questions about how it stays gravitationally bound at all. Some researchers speculate that MK2 might not be a true moon in the traditional sense, but a temporary companion caught in a slow cosmic dance that could one day send it drifting away into space. What makes this enigma so fascinating is how it challenges our understanding of how moons form in the outer solar system. Makemake's solitary existence, save for one shadowy, elusive partner, suggests that the Kuiper Belt operates by rules we're only beginning to grasp. Every time we think we've figured out the pattern, this distant duo reminds us that nature always has another surprise waiting in the dark. The story of MK2 takes an even stranger turn when we examine its orbit, a lopsided, tilted path that defies everything we thought we knew about how moons behave. Most natural satellites, even those in the distant Kuiper Belt, follow relatively flat, circular orbits aligned with their parent world's rotation, but MK2 dances to a different tune. Its path is wildly inclined, tilted at a steep angle that sends it looping far above and below Makemake's equatorial plane. Even more puzzling, its orbit stretches into a pronounced ellipse, swinging from a relatively close 49,000 miles to an astonishing 800,000 miles away at its most distant point. This bizarre trajectory raises a fundamental question. How did MK2 end up in such an unusual arrangement? One possibility is that it wasn't born alongside Makemake at all, but was captured later, a rogue Kuiper Belt object ensnared by gravity. Captured moons aren't uncommon in the outer solar system, but they typically settle into more regular orbits over time. MK2's extreme path suggests either a very recent capture or some unseen force keeping it destabilized. Another theory points to a cataclysmic past. If MK2 formed from debris ejected during a giant impact, like Earth's moon, its odd orbit could be a lingering echo of that violent event. Perhaps the collision was so powerful that it sent the newborn moon careening into this peculiar configuration where it's remained ever since. Then there's the mystery of its darkness. MK2 reflects less than 4% of the sunlight that hits it, making its surface one of the least reflective places in the entire solar system. This pitch-black exterior clashes starkly with Makemake's brilliant sheen, as if the moon is coated in something fundamentally different from its parent world. Some scientists speculate that MK2 might be a primordial relic, a chunk of ancient, carbon-rich material that survived from the solar system's earliest days. Over billions of years, relentless cosmic radiation could have baked its surface into a thick, dark crust of organic compounds, turning it into a shadowy counterpart to Makemake's gleaming eyes. But the plot thickens when we consider how these mysteries intertwine. That extreme orbit might actually explain the moon's darkness. If MK2 spends most of its time far from Makemake, it could be more exposed to space weather radiation and micrometeorites that slowly darken its surface over eons. Alternatively, its tilted path might mean it rarely passes through Makemake's faint, seasonal atmosphere, missing out on any fresh frost that could brighten its appearance. Every clue seems to lead to another layer of questions with no easy answers in sight. What makes MK2 so fascinating isn't just its oddities, but what they reveal, or fail to reveal, about the history of its parent world. That weird orbit could be a smoking gun for ancient chaos, hinting at a time when Makemake's neighborhood was far more violent than the frozen stillness we see today. The moon's darkness might preserve secrets about the raw materials that built the outer solar system, untouched by the processes that sculpted brighter worlds like Makemake itself. Even its lonely existence challenges our models, forcing us to reconsider how moons form and survive in the Kuiper Belt's frigid depths. For now, MK2 remains a cryptic sentinel, circling Makemake in silence, a reminder that even in the farthest reaches of our cosmic backyard, nature still has surprises up its sleeve. Of all the mysteries surrounding Makemake, few are as quietly perplexing as the unexpected heft of this distant world. When scientists first calculated its density, they found something that shouldn't be there, a surprising weight beneath the ice. Most Kuiper Belt objects are fluffy, low-density bodies packed with porous ices that make them more like cosmic snowballs than solid worlds, but Makemake breaks the mold. Its density suggests something far more substantial lurking beneath its gleaming surface, a secret that could rewrite what we know about how these distant worlds formed. The numbers tell the story. Makemake's density sits at around 1.7 grams per cubic centimeter, not far off from Pluto's. That might not sound remarkable until you realize most objects in its neighborhood hover closer to 1.2. This extra mass means Makemake isn't just a simple ball of ice. There's something dense and heavy hidden inside. The leading theory points to a rocky core, a concentrated lump of silicates and metals buried deep beneath the frozen shell. If true, it would mean Makemake underwent a level of differentiation usually seen in much larger planets, with heavy materials sinking to the center while lighter ices rose to the surface. But here's the puzzle. How did a world this small manage such an elaborate internal overhaul? Some researchers argue Makemake might have been warmer in its youth, heated by the decay of radioactive elements in its core. That extra energy could have thawed its interior just enough to let gravity sort the heavy from the light, creating layered structure over billions of years. Others propose a more dramatic origin, a colossal impact early in the solar system's history that blasted away Makemake's outer layers, leaving behind a denser remnant. There's even a wild card idea. What if Makemake isn't a native of the Kuiper Belt at all, but an exiled refugee from closer to the sun? Objects that formed in the inner solar system tend to be rockier, and if Makemake was hurled outward during the planet's chaotic early migrations, it might have carried that dense heritage with it. Yet the mystery deepens when we consider compression. At the extreme pressures found in Makemake's interior, ordinary ices can collapse into exotic high-density forms. Water ice, for instance, can morph into phases like Ice 6 or Ice 7 crystalline structures that behave more like minerals than the familiar frost in your freezer. If enough of Makemake's bulk consists of these ultra-compressed ices, it might not need a large rocky core to explain its density. But this raises another question. What geological forces could have created such intense internal pressure in a world barely 900 miles across? The implications ripple outward. If Makemake truly harbors a significant rocky core, it challenges the long-held idea that Kuiper Belt objects are mostly untouched relics of the solar system's birth. Instead, it suggests even these distant worlds underwent complex evolutionary processes, blurring the line between asteroids, comets, and proper planets. That dense interior might also solve another puzzle: Makemake's unexpected brightness. A rocky core could provide ongoing geothermal heat, subtly reshaping the surface over eons and maintaining its reflective sheen. Or perhaps that hidden mass anchors a subsurface ocean, kept liquid by radioactive decay, with occasional upwellings renewing the ice from below. For now, Makemake keeps its secrets locked away beneath miles of frozen nitrogen and methane. Every theory we have, whether it's a primordial rocky heart, exotic states of ice, or some combination we haven't yet imagined, only underscores how little we truly understand about these distant realms. The next generation of telescopes might finally peel back the layers, revealing whether this icy enigma is more than meets the eye. Until then, Makemake stands as a silent testament to the surprises still waiting in the darkest corners of our solar system. One of the most puzzling contradictions about Makemake is its surface, a vast frozen landscape that looks far too young for its age. In the Kuiper Belt, where cosmic fireworks have been the norm for billions of years, nearly every object bears the scars of countless collisions. Craters should pepper Makemake like bullet holes in a target, yet telescope observations reveal a strangely smooth terrain, with only a handful of dimples marring its otherwise pristine facade. This isn't just unexpected, it's downright baffling. How could an object this old, in a region this violent, manage to stay so unblemished? The leading explanation points to geological resurfacing, some process that's constantly erasing the evidence of impact. On worlds like Jupiter's moon Europa or Saturn's Enceladus, liquid water erupts from subsurface oceans, covering old craters with fresh ice. Makemake might operate on similar principles, but with a twist. Instead of water, its crust could be laced with volatile ices like nitrogen or methane, which soften and flow even at unthinkably cold temperatures. Imagine a glacier in slow motion, but one where the ice is so cold it behaves like putty over geological timescales. A steady oozing of this material could gradually fill in craters, smoothing the surface like cosmic spackle. Yet there's a catch. Most resurfacing mechanisms require an internal heat source, something to keep the engine running. For a small, isolated world like Makemake, that's hard to explain. Radioactive decay in a rocky core might provide just enough warmth to soften shallow layers of ice, but calculations suggest it wouldn't last billions of years. Another possibility is tidal heating, where gravitational interactions flex and warm the interior. But with only one tiny moon in a distant orbit, Makemake lacks the dynamic partners that keep moons like Io or Europa geologically active. Unless, of course, there's something we're missing, like a long-lost moon that once stirred its insides before drifting away. Then there's the wild card, seasonal turnover. Makemake's orbit takes it on a marathon journey around the Sun, lasting over 300 Earth years. As it swings closer to our star, even the faintest sunlight might be enough to vaporize trace amounts of surface ices, redistributing them like a slow-motion snowfall. Over millennia, this cycle could erase smaller craters while leaving only the deepest scars intact. It's a delicate balancing act. Too much activity would make the surface chaotic, while too little would let craters accumulate. Makemake seems to have hit a perfect, improbable middle ground. What makes this mystery so compelling is how it challenges our assumptions about time in the outer solar system. That smooth surface shouldn't exist, yet there it is, gleaming back at us like a cosmic conundrum. Whether it's sluggish ice flows, hidden heat, or some process we haven't yet imagined, Makemake's youthful appearance forces us to reconsider what ancient really means in the deep freeze of the Kuiper Belt. Every theory we devise only deepens the intrigue, leaving us to wonder, is this dwarf planet hiding a geological heartbeat beneath its icy shell? Or are we witnessing the aftermath of some rare cataclysmic renewal event? Until we get closer, that flawless surface remains a silent challenge, a dare to unravel its secrets. Makemake's seasons unfold on a scale almost impossible for human minds to grasp, a slow-motion ballet of ice and darkness dictated by an axial tilt that sends its poles alternating between endless twilight and fleeting sunlight over the course of centuries. Unlike Earth's relatively mild 23-degree tilt, Makemake's axis leans at a dramatic angle, exaggerating its seasonal extremes to almost alien proportions. During its long summer, one pole basks in perpetual but feeble sunlight for decades, while the opposite hemisphere plunges into a deep freeze that would make Antarctica seem balmy. These shifts should leave visible scars, expanding and retreating ice caps, migrating frost patterns, maybe even pockets of temporary atmosphere. Yet observing these changes from Earth is like trying to read a billboard through frosted glass at the edge of twilight. The challenge lies in Makemake's glacial pace. A single seasonal cycle spans roughly 300 Earth years, with each month lasting longer than a human lifetime. By the time telescopes detect a subtle shift in surface brightness or color, multiple generations of scientists may have come and gone. What little we've glimpsed suggests something extraordinary. Nitrogen ice near the summer pole might warm just enough to become slightly mobile, creeping across the landscape like cold syrup before refreezing at the first temperature drop. These sluggish migrations could gradually redistribute surface materials, explaining why Makemake's bright and dark patches appear to shift positions over decades. But the real drama might unfold beneath the ice. Seasonal temperature swings tiny by Earth standards but significant in the Kuiper Belt could fracture the crust, creating pathways for volatile gases to escape. Some researchers speculate these fissures might briefly open vents for nitrogen geysers, similar to Pluto's icy cryovolcanism, before resealing when temperatures drop. Others propose that seasonal pressure changes could activate hidden reservoirs of slushy ammonia water mixtures, squeezing them upward to renew surface ices in slow pulses. The most tantalizing possibility that these cycles drive a form of atmospheric recycling, where trace gases freeze onto winter poles only to evaporate back into space when summer returns, a process that might leave chemical fingerprints detectable by future observatories. What makes these hypothetical changes so revealing is how they differ from other dwarf planets. Pluto's thin but persistent atmosphere stems from its larger size and residual internal heat, while Eris is so distant that even its summers are too cold for significant volatile movement. Makemake sits in the Goldilocks zone, close enough for seasonal effects to matter, but small enough that they'd operate on a knife's edge. If we could monitor its transformations across a full orbit, we might unlock secrets about how volatile compounds behave at the solar system's edge, why some icy worlds cling to atmospheres while others lose them, and whether subsurface chemistry could still be active in these frozen relics. For now, Makemake's seasons remain a silent spectacle, playing out in ultra-slow motion across a stage so distant we can only guess at the script. Makemake's cold is the kind that defies logic, a deep, unnatural chill that lingers even by the frozen standards of the Kuiper Belt. Theoretical models predicted it would hover around -240 degrees Celsius, already colder than Pluto's icy plains. But when astronomers measured its actual temperature, the readings plunged even lower, scraping uncomfortably close to absolute zero. This isn't just a slight discrepancy, it's a thermal anomaly that shouldn't exist, as if Makemake has somehow found a way to cheat the universe's heat budget. The leading explanation points to its uncanny brightness. Most objects in the outer solar system are dull and dark, absorbing sunlight like cosmic sponges and radiating the energy as heat. Makemake, by contrast, acts like a mirror, reflecting nearly 80% of the feeble sunlight that reaches it, far higher than Pluto or Eris. That reflectivity, combined with its lack of a substantial atmosphere to trap warmth, could turn its surface into a refrigerator, actively shedding what little heat it receives back into space. But this raises another question. Why doesn't its lone moon, MK2, which shares the same environment, exhibit the same extreme cold? The discrepancy suggests Makemake's frigid nature isn't just about location, it's something intrinsic to the world itself. Then there's the wild card of internal heat, or rather, the lack of it. Many dwarf planets like Pluto maintain residual warmth from their formation or radioactive decay, which subtly influences surface temperatures. Makemake's unexpected cold could imply its core went dormant earlier than expected, shutting down any geothermal activity that might have once provided a faint heat source. Alternatively, its high reflectivity might insulate it too well, preventing external heat from penetrating deep enough to trigger geological processes that could sustain warmth. The most tantalizing possibility, Makemake's surface chemistry might be playing tricks on thermodynamics. Certain exotic ices, like crystalline nitrogen or methane clathrates, can conduct heat in bizarre ways under extreme conditions, not unlike how a thermos flask keeps liquids hot or cold by disrupting normal energy transfer. If Makemake's crust contains layers of these materials arranged in just the right configuration, it could effectively act as a planetary-scale insulator, locking in the cold like a cosmic deep freeze. Yet every hypothesis comes with its own contradictions. If Makemake's reflectivity drives its coldness, why do other bright Kuiper Belt objects like Haumea not exhibit such extreme temperatures? If its interior is geologically dead, how does it maintain such a young-looking surface? The deeper we dig, the more this thermal paradox seems tied to other mysteries: its density, its absent atmosphere, even its peculiar moon. For now, Makemake's cold remains a puzzle wrapped in layers of ice, a reminder that even in the darkest corners of the solar system, nature still has ways to surprise us. If there's one thing that makes Makemake stand out in the frozen gallery of Kuiper Belt objects, it's what's not there: the glaring absence of certain ices that coat nearly every other world in its neighborhood. While Pluto glistens with nitrogen frost and Eris wears a blanket of methane, Makemake's surface appears oddly selective, missing vast deposits of these volatile compounds that should, by all rights, dominate its frozen landscape. This isn't just a minor discrepancy, it's a cosmic whodunit, a case of vanishing materials that leaves scientists scratching their heads. The mystery starts with basic chemistry. Methane and nitrogen are the lightweights of the outer solar system, ices so delicate they can vaporize even in the feeble warmth of distant sunlight. On larger worlds like Pluto, gravity helps trap these materials, creating stable surface deposits and wispy atmospheres. But Makemake straddles a precarious middle ground, big enough to retain some volatiles, yet small enough that escape might still win out. The leading theory, sublimation, the process where solids turn directly to gas in the vacuum of space, could be slowly bleeding these ices away. Over billions of years, even the faintest solar heat might have stripped Makemake's surface layer by layer, leaving behind only the hardier water ice and darker organic residues. Yet there's a twist: Makemake does show traces of methane, just not where or how we'd expect. Instead of sprawling plains of frost, spectral analysis reveals methane locked in an unusual chemical marriage, bonded with nitrogen or trapped in water ice cages called clathrates. This suggests a world where volatiles didn't simply disappear but underwent dramatic transformations. Radiation from cosmic rays could have broken methane molecules apart, reassembling them into complex hydrocarbons that stain the surface reddish-brown. Nitrogen, meanwhile, might have retreated underground, forming hidden reservoirs beneath an insulating crust. The plot thickens when we consider time. Makemake's elliptical orbit means its distance from the Sun varies dramatically over its 300-year year. During closer approaches, even slight temperature spikes could trigger violent outbursts of volatile loss. Imagine dry ice vanishing in a cloud of fog, but on a planetary scale. These seasonal purges might explain why fresh-looking patches occasionally appear in telescope data, as if entire regions of ice suddenly collapsed into space. Compounding the puzzle is Makemake's reflectivity. Its brilliant surface should act like a mirror, bouncing back sunlight that might otherwise warm and sublimate ices. Somehow, despite this protection, the volatiles still vanished. Perhaps the most tantalizing clue lies in Makemake's density. That surprisingly hefty interior we discussed earlier could hold the key. If the dwarf planet's core generates even faint geothermal warmth, it might create a slow conveyor belt of ice volatiles migrating downward to liquefy at depth, only to resurface eons later in altered form. This could explain why we see methane in odd configurations rather than pure deposits. It's been chemically processed in unseen laboratories beneath the crust. Alternatively, Makemake's missing ices might point to an origin story unlike its neighbors. If it formed farther from the Sun than Pluto or Eris, its initial inventory of volatiles could have been sparser from the start, leaving it with less to lose. What makes this enigma so compelling is how it connects to broader mysteries. Those absent ices might explain Makemake's lack of atmosphere, its thermal anomalies, even the bizarre darkness of its moon. Every missing molecule tells a story, one of escape, transformation, or concealment. For now, the surface keeps its secrets, a frozen palimpsest where the original writing has faded, leaving only cryptic traces of what once was. Until a spacecraft visits this distant world, we're left piecing together clues from the faintest whispers of reflected light, trying to reconstruct a history written in ice that refuses to stay put. Most dwarf planets in the outer solar system spin with the sluggish grace of aging ballerinas, completing rotations so slow you could practically watch them move. Then there's Makemake, a cosmic speed demon pirouetting at a pace that defies expectations. Clocking a day lasting just 7.5 hours, this distant world whirls faster than any object its size has any right to. For context, Pluto takes 6 Earth days to complete a single rotation. Eris, another Kuiper Belt heavyweight, spins once every 25 hours. Even Earth, significantly denser and more compact, takes 24. Makemake's breakneck speed presents a thorny puzzle. What set this frozen world spinning like a top in the vast stillness of space? The implications ripple outward, starting with shape. Centrifugal force from rapid rotation should flatten Makemake noticeably, stretching it into an oblong spheroid wider at the equator than the poles. Think of a ball of dough spun until its edges flare outward. Yet preliminary observations suggest its deformation isn't as extreme as physics predicts. This discrepancy hints at something unusual beneath the ice, perhaps a dense, rigid core anchoring the dwarf planet's structure against the distorting effects of its spin. Alternatively, the surface ices themselves might behave unexpectedly under such forces, flowing just enough to redistribute mass without dramatic bulging. Either scenario implies an interior far more complex than the simple balls of ice and rock we once imagined for Kuiper Belt objects. Then there's the question of origins. Conventional formation models suggest objects like Makemake should have slower spins, their rotations gradually dampened over eons by gravitational interactions and collisions. A rotation this fast implies either a violent past a colossal impact that sent it careening, or an unusual lack of the usual braking mechanisms. The collision theory carries weight. Earth's moon likely formed when a Mars-sized object slammed into our planet, and the debris coalescing into lunar material would have spun rapidly initially. But Makemake shows no obvious signs of such trauma, like a system of moons or a drastically irregular shape. The alternative, that it avoided the typical slowdown, is equally perplexing. Did it form in an unusually sparse pocket of the Kuiper Belt, missing the traffic of smaller objects that normally sap rotational energy over time? Or does its strange orbit play a role, minimizing gravitational nudges from Neptune or other large bodies that could have stabilized its spin? The mystery deepens when we consider energy distribution. Fast rotation often correlates with geological activity. Think of Jupiter's volcanic moon Io, whose orbit keeps its insides churning. Yet Makemake's surface appears relatively calm, lacking clear evidence of the fractures or cryovolcanism we'd expect from a world under such centrifugal stress. Unless, of course, that energy is channeled invisibly, liquefying layers of subsurface slush or maintaining hidden pockets of pressurized gas that occasionally vent to refresh the surface. There's even a speculative possibility that Makemake's spin isn't constant. Some distant objects exhibit spin-up over time, their rotations accelerating as sunlight sublimates surface ices asymmetrically, a process called the Dwarf effect. If Makemake's reflective patches aren't evenly distributed, photons bouncing off its surface could act like tiny thrusters, nudging it faster millimeter by millimeter over millions of years. What makes this enigma so compelling is how it connects to other mysteries. That brisk rotation could help explain the uneven distribution of surface ices, flinging volatile materials toward the equator while leaving poles bare. It might contribute to the absence of a permanent atmosphere, with centrifugal force slinging escaping gases into space more efficiently. Even Mk2's odd orbit could be a relic of the dwarf planet's spin history, a moon struggling to find stability around a host that refuses to slow down. Every clue intertwines, painting a portrait of a world that dances to rhythms we're only beginning to hear. For now, Makemake keeps spinning its secrets in the dark, a frozen enigma whirling through questions faster than we can answer them. Peering beneath Makemake's icy shell is like trying to decipher a message written in smoke. Every clue seems to slip away before we can grasp it. Unlike larger worlds where gravity tugs on passing spacecraft, revealing secrets of their internal structure, this distant dwarf planet offers no such easy answers. Yet the few hints we've gathered paint a portrait far more complex than a simple ball of ice. The key lies in Makemake's density, that unexpected heft we discussed earlier, which suggests something dense and heavy anchors its core. But what exactly lurks beneath those frozen plains? One compelling scenario points to a differentiated interior, a layered structure where heavier materials like rock and metal sank to the center while lighter ices rose to the surface. This process, common in larger planets, requires enough internal heat to melt and separate materials early in a world's history. For Makemake, that heat might have come from radioactive elements like potassium-40 or thorium-232, their decay warming the interior just enough to trigger chemical sorting over billions of years. If true, it would mean this small world harbors a miniature version of Earth's own iron core, wrapped in a mantle of high-pressure ice and topped by that gleaming outer shell. The implications are staggering. It would place Makemake in an exclusive club of geologically sophisticated worlds, defying the old notion that Kuiper Belt objects are primordial snowballs. But there's a twist. Some models propose that Makemake's density could stem not from rock, but from exotic forms of compressed ice. At the crushing pressures found deep inside even small icy bodies, water molecules reorganize into bizarre configurations, ices with Roman numerals like Ice 2 or Ice 5, each denser than the last. If Makemake's interior is a labyrinth of these ultra-compressed crystals, it might explain the extra weight without requiring a large rocky core, the catch. Such ices typically form under conditions more extreme than Makemake's size should generate, raising new questions about how it achieved such intense internal pressures. Then there's the wildcard possibility: subsurface oceans. On moons like Europa and Enceladus, tidal forces from giant planets keep water liquid beneath miles of ice. Makemake lacks such dynamic partners, but its potential rocky core could host another heat source: radioactivity. If enough uranium or thorium concentrates in its center, the slow decay might maintain pockets of briny slush sandwiched between layers of ice. The chemistry would be alien, a mix of ammonia, salts, and organic compounds, lowering the freezing point to unimaginable lows. While evidence is scant, the idea isn't pure fiction. Pluto's suspected subsurface ocean proves even distant dwarf planets can defy expectations, and Makemake's youthful surface might hint at occasional upwellings of liquid renewing the ice from below. The greatest challenge in solving this puzzle is the sheer lack of tools to probe it. Earth-based telescopes can measure Makemake's bulk density, but distinguishing between a rocky core and compressed ices requires detecting subtle gravitational signatures, something only a visiting spacecraft could achieve. Even then, the ice shell's thickness and composition would dramatically alter how heat flows from the interior, masking clues about what lies deeper. Some researchers have proposed listening for cryoseismic activity, icequakes that might ripple through the crust, betraying the presence of liquid layers beneath. Others suggest hunting for trace gases like methane or nitrogen seeping from fractures, which could indicate geothermal vents stirring below. What makes this mystery so tantalizing is how it connects to every other enigma surrounding Makemake. That possible rocky core might explain its rapid spin, acting as a dense flywheel keeping the world whirling. Hidden liquids could feed sporadic resurfacing, maintaining those puzzling bright plains. Even the missing atmosphere might trace back to subsurface processes, with gases escaping through cracks only to freeze out again in seasonal cycles. For now, Makemake's interior remains a shadowy realm of possibilities, a reminder that even in the solar system's farthest reaches, complexity thrives in the dark. One of the most overlooked yet fascinating oddities about Makemake isn't what's there, but what isn't. Unlike nearly every other similarly sized object in the Kuiper Belt, this dwarf planet shows no trace of surrounding dust or debris. No faint rings, no diffuse clouds of impact fragments, not even the occasional sparkle of micrometeoroids catching sunlight. It's as if Makemake exists in a cosmic clean room, defying the chaotic environment it calls home. This absence speaks volumes because in a region where collisions are as common as raindrops on Earth, such pristine conditions shouldn't exist without explanation. The first clue lies in the numbers. The Kuiper Belt is essentially a demolition derby frozen in slow motion, with objects constantly smashing into one another over billions of years. These collisions, even small ones, should kick up clouds of dust and debris that linger for millennia. Pluto, for instance, shows evidence of ongoing impacts in its system, with faint rings hinted at in New Horizons data. Even smaller objects like Haumea sport debris disks from ancient smash-ups, yet Makemake's immediate vicinity appears eerily empty, as if some unseen hand has swept the area clean. One possibility is that Makemake has simply been lucky or unlucky depending on perspective. Statistical models suggest that over its lifetime, it should have experienced at least a dozen significant collisions capable of generating visible debris. If none of those happened recently, the evidence might have dissipated over time, but this stretches plausibility. At Makemake's distance, where solar radiation and planetary flybys are weak, debris should accumulate like snowdrifts, not vanish without a trace. That leaves a more intriguing alternative. Something is actively scrubbing the area clean. The prime suspect, Makemake's potential transient atmosphere. While inconsistent in modern observations, seasonal outgassing could create a faint but persistent envelope of nitrogen or methane around the dwarf planet. Even a wispy atmosphere would act like a cosmic broom, dragging dust particles down to the surface through gentle but constant friction. On larger worlds like Pluto, this process is too slow to matter, but Makemake's smaller size and gravity might make it just efficient enough to keep its orbit spotless. Then there's the wild card of electrical forces. In the deep cold of the Kuiper Belt, ice grains can build up significant static charges. If Makemake's surface holds an electrostatic field, perhaps from constant bombardment by cosmic rays, it might repel or attract dust in ways we don't yet understand. Similar phenomena have been observed on Saturn's icy moons, where charged particles create bizarre dust highways in the planet's magnetic field. Without a spacecraft to measure such effects directly, we're left guessing whether Makemake's environment plays by similar rules. What makes this absence so compelling is how it connects to other mysteries. A dust-free zone could explain why Makemake's surface stays so unnaturally bright. No dirty snowballs constantly raining down to darken its facade. It might also hint at ongoing geological activity, where escaping gases not only clear debris but subtly resurface the world in the process. Or perhaps it's evidence of something more exotic, like a long-gone moon whose breakup flung debris far beyond detection, leaving only whispers of its passing in Makemake's oddly tidy orbit. For now, this pristine emptiness stands as another quiet defiance of expectations, a reminder that even in the solar system's most chaotic neighborhood, some worlds insist on keeping their corners impeccably clean. Whether through hidden atmospheric tricks, unseen forces, or sheer cosmic coincidence, Makemake's spotless surroundings challenge us to rethink how small, icy worlds evolve, and what secrets they might still be sweeping under the rug. When astronomers point their spectrometers at Makemake, they don't just see another bland, icy world. They're greeted by a cosmic fingerprint that refuses to fit the usual templates. The light bouncing off its surface carries a peculiar mix of absorption bands and reflective properties unlike anything else in the Kuiper Belt. Where Pluto's spectrum screams methane and Eris shows textbook water ice signatures, Makemake's data is an enigmatic cocktail, hints of methane without the expected strength, traces of nitrogen that come and go between observations, and an odd red slope in its infrared readings that suggests something far more complex is at play. Take methane, for instance. On most icy worlds, this simple hydrocarbon leaves deep, unmistakable troughs in spectral graphs, clear evidence of abundant surface frost. Makemake's methane signature exists, but it's strangely muted, as if the molecules are being muffled. One explanation points to grain size. Unlike the fluffy methane snow covering Pluto, Makemake's version might be locked into coarser, compacted crystals that scatter light differently. Another theory suggests chemical bonding, methane molecules trapped in nitrogen ice cages or chemically altered by radiation into unfamiliar forms. Then there's the wildcard idea. What if Makemake's methane isn't native at all, but delivered by cometary impacts, leaving only a thin veneer that never fully integrated with the surface? The nitrogen puzzle is even thornier. Early spectra suggested its presence, but follow-up studies failed to confirm it consistently. This disappearing act implies nitrogen isn't evenly distributed, perhaps hiding in isolated patches that rotate in and out of view, or buried beneath a translucent layer of other ices. On Pluto, nitrogen dominates entire glaciers, but Makemake seems to ration it sparingly, as if the dwarf planet can't decide whether to showcase or conceal it. The volatility of nitrogen adds another wrinkle. At Makemake's extreme temperatures, this ice should sublimate directly from solid to gas with even slight warming, making its sporadic appearances all the more baffling. But the real head-scratcher is that infrared slope, the gradual reddening of Makemake's spectrum at longer wavelengths. Most icy objects reflect evenly across these bands, but Makemake darkens progressively toward the red, a trait usually associated with complex organic compounds. The leading suspect, tholins, those reddish-brown molecules formed when simple hydrocarbons like methane are cooked by cosmic radiation over eons. These substances paint other outer solar system worlds, including Pluto's iconic reddish patches, but Makemake's version seems oddly concentrated in spectral data without obvious surface markings to match. This suggests the tholins might be finely distributed or mixed with other materials in ways that alter their usual spectral voice. Compounding the confusion is Makemake's reflectivity. Normally, tholins and other dark organics dampen a world's brightness dramatically, yet Makemake remains one of the shiniest objects known. This paradox hints at surface renewal processes actively counteracting the darkening effects. Perhaps cryovolcanic plumes spray fresh ice over tholin-stained terrain, or seasonal frosts bury the organics under temporary bright blankets. There's even a chance Makemake's tholins are fundamentally different, less carbon-rich or mixed with reflective ices in microscopic combinations that confuse our instruments. What makes this spectral mystery so compelling is how it intertwines with Makemake's other oddities. That erratic rotation could churn surface ices, creating spectral variations that shift hourly. The high density might point to mineral contaminants subtly altering absorption bands. Even the absent debris field could factor in without constant dustfall. Makemake's surface chemistry evolves in isolation, free from the contamination that affects dustier neighbors. Every attempted explanation feels like turning a kaleidoscope, one slight adjustment, and the entire pattern shifts. For now, Makemake's light remains a cipher, a message we lack the key to fully decode. Future telescopes with advanced spectrographs may tease apart these riddles, revealing whether we're seeing exotic chemistry, geological artistry, or something entirely unanticipated. Until then, this distant world keeps its secrets written in wavelengths, a spectral sonata played just beyond our current comprehension. Makemake's surface behaves like a shattered mirror, some patches reflecting sunlight with almost perfect efficiency while others absorb it like cosmic velvet. This bizarre variation in albedo or reflectivity isn't just random noise. It follows geometric patterns that have astronomers puzzled. Most icy worlds show gradual brightness changes tied to terrain or composition, but Makemake's sharp albedo boundaries look like someone drew them with a ruler, dividing the surface into distinct zones of light and dark with unnatural precision. The contrast is striking. Certain regions bounce back nearly 90% of incoming light, brighter than freshly fallen snow on Earth, while adjacent areas dip below 30%, darker than asphalt. This isn't merely a matter of some slopes facing away from the sun. The changes happen across flat terrain with identical lighting conditions. The leading theory suggests a two-tiered surface process, some mechanism actively renewing the bright zones while leaving others to accumulate darker materials over time. On Pluto, similar bright patches occur where nitrogen ice sublimates and recondenses in endless cycles. But Makemake lacks both the atmospheric pressure and consistent heat sources to drive comparable activity. An even more intriguing possibility involves cryovolcanic paints. If isolated geysers or fractures spew nitrogen or methane-rich slurries onto specific regions, the rapidly freezing liquids could form ultra-smooth plains that scatter light with mirror-like efficiency. The darker areas might represent older terrain where radiation has cooked surface ices into complex organics. But this raises another puzzle. Why would such resurfacing be so localized? Most cryovolcanic worlds erupt fairly evenly across their surfaces, yet Makemake's refreshment appears almost intentional, concentrated in geometric patterns that defy typical geological models. The plot thickens when examining spectral maps. Those eerily precise albedo boundaries often align with subtle compositional shifts, slightly more methane in bright zones, traces of tholins in darker ones. This implies the reflectivity variations aren't just surface texture differences but fundamental chemical divides. One radical hypothesis suggests Makemake might have experienced a lopsided impact so violent it partially remelted one hemisphere, allowing lighter ices to resurface half the world before refreezing into this patchwork. Others propose tidal stresses from a past close encounter with Neptune could have cracked the crust in specific orientations, creating preferential pathways for volatile migration. What makes this mystery so compelling is how it connects to other enigmas. Those geometric bright zones could explain the dwarf planet's overall high reflectivity, their contribution outweighing darker regions in global measurements. The sharp albedo boundaries might also hint at subsurface structures with hidden faults or composition layers influencing surface renewal patterns. Even Makemake's spin comes into play, its rapid rotation potentially channeling ices toward the equator while leaving poles bare. Every attempt to decode these reflective puzzles just leads deeper into the labyrinth, revealing a world that doesn't just defy expectations, it seems to rewrite the rules entirely. Most icy worlds in the outer solar system put on a show, geysers erupting from Enceladus, nitrogen glaciers flowing across Pluto, even the occasional dusty puff from distant comets. Yet Makemake sits in stubborn silence, its frozen surface showing no signs of the volatile outbursts that define its neighbors. This absence isn't just curious, it's a glaring contradiction. With a composition similar to Pluto and Eris, packed with ices that should vaporize under the faintest solar warmth, Makemake should be spewing gases like a cosmic tea kettle. Instead, it's eerily inert, a frozen sphinx keeping its secrets locked in ice. The mystery starts with simple physics. At Makemake's distance, sunlight is barely more than a dim glow, but even that meager energy can transform surface ices. On Pluto, nitrogen and methane sublimate directly from solid to gas, creating a wispy atmosphere and fueling landscape changes. Comets closer to the Sun erupt dramatically, their surfaces cracking open as trapped gases explode into space. Makemake's ingredients are just as volatile, so why no fireworks? One possibility cuts to the core. Maybe its ices aren't as exposed as we think. Spectra suggest methane might be chemically bonded or trapped in other ices, preventing it from escaping easily. Alternatively, the dwarf planet's high reflectivity could act like a thermal blanket, bouncing back sunlight before it penetrates deep enough to trigger sublimation. But there's a darker scenario. What if Makemake already bled itself dry? Over billions of years, even slow leaks add up, without internal heat to replenish lost volatiles. No active geology, no tidal flexing. The dwarf planet might have exhausted its reserves, leaving behind an icy fossil stripped of the materials needed for outgassing. This would make it a tragic figure among dwarf planets, a world that once had the potential for Pluto-like dynamism but now lingers as a frozen relic. Yet the plot twists when we consider seasonal extremes. Makemake's elliptical orbit means its distance from the Sun varies by nearly 1 billion miles. During its closest approaches, temperatures might spike just enough to awaken dormant ices. If gases only escape during these rare warm spells, we could be looking at the wrong time, like checking a volcano during its centuries-long slumber. Some researchers hold out hope for sporadic activity, with telescopes catching the occasional wisp of nitrogen or methane when conditions align. The implications ripple beyond curiosity. A Makemake that never outgassed suggests a fundamentally different history, perhaps forming in a colder, quieter part of the protoplanetary disk where volatiles were scarcer. One that lost its gases hints at how even dwarf planets can age into quietude, their geological clocks winding down. And if outbursts are merely episodic, it challenges our assumptions about what counts as active in the deep freeze of the Kuiper Belt. For now, the dwarf planet keeps its silence, a testament to how much we still don't understand about the lives of icy worlds at the solar system's edge. The solar wind, a relentless stream of charged particles blasting outward from the Sun at 1 million miles per hour, should be battering Makemake like a cosmic sandblaster. Yet observations reveal something odd. This distant dwarf planet interacts with these particles in ways that defy every expectation. Without a substantial atmosphere to act as a buffer and no detectable magnetic field to deflect the onslaught, Makemake should be a sitting duck for solar wind erosion. Instead, it's as if the solar wind barely leaves a mark, raising the question what invisible shield is protecting this icy world. One clue lies in the dwarf planet's reflectivity. That mirror-like surface might be doing more than just bouncing back sunlight. It could be creating an unexpected barrier. When highly energetic particles slam into ultra-smooth ice, they don't always penetrate. Instead, they scatter like bullets ricocheting off armor. If Makemake's surface is as polished as data suggests, it might be effectively deflecting a significant portion of the solar wind through sheer geometry. This wouldn't explain everything, but it hints that the dwarf planet's exterior isn't just passively freezing. It's actively engineered by conditions we don't fully understand. Then there's the enigma of transient gases. Even if Makemake lacks a permanent atmosphere, seasonal outgassing could provide brief pockets of protection. When nitrogen or methane frost warms slightly, escaping molecules might form a temporary ionosphere, a thin layer of charged particles that interacts with the solar wind in unpredictable ways. These fleeting interactions could create localized magnetic disturbances, bending incoming particles around the dwarf planet like water flowing around a boulder. It's a delicate dance, one that might only happen in sporadic bursts, making it nearly impossible to catch in action from Earth. But the real curveball comes from Makemake's spin. That rapid rotation might be generating weak but pervasive electrical currents in its icy crust. On larger worlds, such currents typically induce magnetic fields, but Makemake's small size likely prevents that. Instead, these currents could distort the solar wind's path in subtler ways, creating turbulence that dissipates energy before it reaches the surface. It's akin to how a spinning top disrupts the air around it, just on a planetary scale. What makes this mystery so intriguing is how it challenges our understanding of space weather. If a world as seemingly defenseless as Makemake can resist solar wind erosion through a combination of surface properties, fleeting gases, and rotational quirks, it forces us to reconsider how other small, icy bodies survive in the cosmic storm. Perhaps there's an entire class of unseen interactions at play in the outer solar system mechanisms that don't fit our current models. For now, Makemake stands as a silent rebel, defying the solar wind in ways we're only beginning to glimpse, its secrets written in particles we can't yet see. Every world has a birth story, but Makemake's reads like a cosmic whodunit with too many suspects and not enough clues. Unlike planets that formed in orderly disks around the young sun, this distant dwarf planet's origin remains stubbornly opaque, caught between competing theories that each raise as many questions as they answer. The central debate hinges on location. Did Makemake form right where it sits today, a frozen sentinel of the Kuiper Belt, or was it born closer to the sun before being hurled outward in the solar system's chaotic youth? The evidence refuses to settle neatly either way, leaving astronomers to piece together conflicting clues like detectives at an unsolved crime scene. On one side stands the in situ formation theory, the idea that Makemake coalesced from the primordial soup of ice and rock that once swirled beyond Neptune. Its composition fits the neighborhood, rich in methane and nitrogen like other Kuiper Belt objects. Yet this seemingly straightforward explanation stumbles over Makemake's peculiar density. Most native Kuiper Belt bodies are porous rubble piles with densities barely exceeding water ice, but Makemake's surprising heft suggests a significant rocky component. That's hard to reconcile with formation in a region where lightweight ices dominate, unless, of course, the dwarf planet somehow gathered more than its share of heavy elements, a cosmic lottery win with no clear mechanism. Enter the scattering hypothesis. This alternate origin story casts Makemake as an exile, born in the warmer inner solar system before gravitational encounters with giant planets launched it outward. The math holds up during the so-called late heavy bombardment around 4 billion years ago. Neptune's migration likely ejected thousands of objects into the Kuiper Belt. Makemake's density aligns better with inner solar system bodies like Pluto, which share its rock-rich composition, but here too inconsistencies emerge. Scattered objects typically end up in more elliptical and inclined orbits, yet Makemake's path around the Sun is relatively circular and flat compared to other displaced worlds. It's as if the dwarf planet gently parked itself rather than being violently ejected. The plot thickens when considering Makemake's missing volatiles. Objects that formed farther out should have retained more primordial methane and nitrogen, yet Makemake seems oddly depleted, almost as if it started life in warmer climes where these ices were scarcer. But then, why does its surface show such sophisticated processing of the volatiles it has, with methane bonded into complex arrangements? One radical proposal suggests a hybrid origin. Perhaps Makemake formed at the Kuiper Belt's inner edge, where temperatures allowed partial retention of volatiles while still accumulating enough rock to explain its density. This Goldilocks scenario would make it neither a true local nor a classic interloper, but something in between a borderland world with an identity crisis. Perhaps the most tantalizing clue lies in Makemake's solitary moon. Most scattered objects retain multiple satellites from their violent pasts, while native Kuiper Belt objects often sport debris disks from gentler collisions. MK2's darkness and odd orbit don't neatly fit either pattern. Its existence could imply a middle path, a glancing encounter that nudged Makemake outward without the extreme violence that typically strips moons away. Or maybe MK2 is the last survivor of a once larger system, its siblings lost to the depths of space over eons. What makes this mystery so compelling is how it forces us to reconsider the solar system's early chaos. Makemake might be a Rosetta Stone for understanding planetary migration, its current orbit and composition preserving faint echoes of ancient gravitational dances. Every new observation adds wrinkles to the story, from its unexpectedly youthful surface to those perplexing spectral signatures. Until a spacecraft visits this distant world, measuring isotopes in its ices or mapping subsurface structures, its origin will remain suspended between possibilities, a cosmic Schrödinger's cat simultaneously local and alien, its true history locked beneath miles of ice waiting to be read. Out in the Kuiper Belt, cosmic companionship is practically the norm, worlds twirling around each other like dancers in the darkness, locked in gravitational embraces that last billions of years. Pluto has Charon, Haumea spins with 2 moons, even smaller objects like Lempo and Patroclus orbit each other as equals. Yet Makemake stands apart, drifting in solitary silence with only its tiny, enigmatic moon Mk2 for company. This isolation isn't just lonely, it's statistically bizarre, a cosmic outlier that refuses to follow the rules of its neighborhood. The numbers tell the story. Over half of all known Kuiper Belt objects larger than 600 miles have binary partners, near twin worlds formed together from the same swirling cloud of ice and dust. Smaller objects pair up even more frequently, with some estimates suggesting up to 80% of mid-sized Kuiper Belt residents have companions. Makemake's singular existence flies in the face of these odds, making it one of the only major dwarf planets without a binary partner. The question isn't just why, it's how this solitary state could persist for billions of years in a region where gravitational interactions should have nudged it into some kind of partnership. One theory points to a violent past. Binary systems often form through gentle collisions, where 2 proto-worlds graze each other and end up gravitationally bound. If Makemake experienced a more catastrophic impact, a head-on smash that vaporized its potential partner, it might explain both its lonely state and the peculiar nature of Mk2. That dark, irregular moon could be the sole survivor of the wreckage, a fragment flung into orbit while the rest of the debris scattered into space. Supporting this idea is Makemake's surprisingly high density, which hints at a history of extreme collisions that might have stripped away lighter materials and any would-be binary companions. Then there's the gravitational escape hypothesis. The Kuiper Belt isn't static. Neptune's influence stirs the region like a slow-motion whirlpool, perturbing orbits over eons. Computer simulations suggest many binary pairs in the outer solar system get torn apart by these subtle nudges, with one partner drifting away forever. Makemake might have once had a twin that was stolen by a close encounter with Neptune or another massive object, leaving it abruptly alone. This scenario could also explain Mk2's distant, unstable orbit. Perhaps it's the last frayed thread of a once tighter system, barely clinging to its parent world after the primary companion was lost. But the most tantalizing possibility involves Makemake's location. Unlike Pluto and Eris, which orbit closer to Neptune's gravitational reach, Makemake hugs the outer edge of the Kuiper Belt's cold classical population, objects with stable, nearly circular orbits that have likely remained undisturbed since the solar system's birth. This region is oddly sparse in binary systems compared to the inner Kuiper Belt, suggesting formation conditions might have differed. If Makemake coalesced in a part of the protoplanetary disk where material was too thinly spread for binary formation, its solitude could be primordial, a relic of the solar system's patchy infancy. The implications ripple outward. That missing binary partner might hold the key to other mysteries like Makemake's unusually high reflectivity. Binary systems tend to darken over time as mutual tidal forces churn up subsurface material, exposing darker layers. Without a partner to stir its insides, Makemake's surface could have remained pristinely bright, untouched by the geological upheavals that weather its neighbors. Even the dwarf planet's rapid spin fits the pattern. Binary companions often slow each other's rotation through gravitational drag, meaning a lone Makemake might have retained its original, faster pirouette. What makes this absence so compelling is how it defies simple categorization. most solar system anomalies come down to what's there: an unexpected moon, a bizarre surface feature, an anomalous orbit. Makemake's mystery is defined by what isn't there, a cosmic negative space that whispers of lost partners, violent beginnings, or perhaps an entirely different origin story than its peers. Until we send a probe to this distant world, its solitude remains one of the Kuiper Belt's quietest but most profound puzzles, a reminder that sometimes what's missing speaks louder than what's present. Imagine standing on Makemake's frozen plains as dawn creeps across the horizon, except this sunrise lasts decades, and the weather is something out of a fever dream. With temperatures hovering near absolute zero and an atmosphere thinner than Earth's exosphere, you wouldn't expect meteorological drama. Yet hidden forces might be sculpting this world in slow motion, frost creeping like glacial shadows, gases whispering over ice in patterns we can barely fathom. The paradox is tantalizing. A place seemingly frozen in time might harbor weather systems stranger than any hurricane or blizzard on Earth. Start with frost migration. On Pluto, nitrogen and methane ices shuffle across the surface with the seasons, forming heart-shaped glaciers that crawl millimeters per year. Makemake's exaggerated axial tilt and elliptical orbit create even more extreme seasonal swings, centuries-long summers where fleeting sunlight could nudge volatile ices just enough to make them creep. Here's the twist: without a thick atmosphere to distribute heat evenly, these frost movements wouldn't blanket the globe but cluster in jagged, unpredictable patches. Picture nitrogen snowbanks piling up along crater rims where shadows trap cold, or methane hail forming in micrometer-thick layers during rare temperature spikes. Unlike Earth's weather driven by air and water, Makemake's would be a silent ballet of sublimation and refreezing ices vanishing from one region only to reappear elsewhere, like a magic trick played at geological speed. Then there's the enigma of wind. Makemake's wispy atmosphere, if it exists at all, should be too thin to carry even a dust grain. But extreme temperature gradients could generate sporadic breezes where gases briefly mobilize. Near the terminator line dividing day and night, a temperature difference of just 10 degrees might create kilometer-high columns of rising nitrogen gas, sparking ultra-slow convection currents. These winds wouldn't howl, they'd barely stir a molecule-thin mist, but over millennia, they could redistribute surface ices in measurable patterns. Even more bizarre, electrostatic forces might loft fine ice particles, creating a form of airborne transport without traditional weather. On Earth, wind shapes dunes. On Makemake, it might sculpt microscopic ridges invisible to telescopes. Detecting these phantom weather systems is like trying to photograph a glacier with a single snapshot per century. Our best clues come from Makemake's inconsistent reflectivity, bright patches that appear, vanish, or drift between observations. Some researchers interpret these as frost deposits migrating with seasons, lasting longer than the Renaissance. Others point to subtle color changes in Hubble data, where reddish organic compounds seem to concentrate in certain areas over time, as if carried by unseen currents. The darkest secret: Makemake's weather might operate in stops and starts. During rare orbital perihelion, a surge of solar energy could trigger temporary nitrogen geysers or methane fog banks, phenomena lasting just years before the world lurches back into deep freeze. What makes this speculation so electrifying is how it redefines weather entirely. Forget storms and rain here. The meteorological drama unfolds in the slow creep of ices, the occasional sigh of escaping gases, and the invisible hand of electrostatic forces. For a world we once wrote off as static, these hypothetical patterns hint at a dynamism hiding in plain sight, waiting for future missions to peel back the layers of frost and time. Until then, Makemake's unseen weather remains a ghostly presence, a whisper of movement in the void. Among Makemake's many riddles, few are as visually haunting as the faint, ghostly streaks that spiderweb across its surface, elongated markings so subtle they flirt with the edge of detectability. These linear features, glimpsed in the highest resolution telescope images, don't resemble the chaotic crater scars of most icy worlds. Instead, they form loose networks of parallel lines, like scratches from a cosmic claw or the cracked glaze of an antique ceramic globe. Their very existence defies easy explanation, presenting a menu of possibilities, each more intriguing than the last. Start with tectonics. On Earth, linear faults often trace the boundaries between shifting crustal plates, but Makemake lacks the internal heat for traditional plate tectonics. Yet its surprisingly high density hints at a rocky core that might still radiate faint warmth enough, perhaps, to trigger slow-motion cracking as the icy shell contracts over billions of years. Imagine the surface as a frozen lake at midnight, ice groaning as temperature drops create hairline fractures. Now scale that up to planetary dimensions, with cracks propagating at centimeters per millennium, their paths guided by variations in ice thickness or composition. These fractures wouldn't be jagged like earthquake faults, but smoothed by the plastic flow of ice under pressure, leaving behind the elegant scars we glimpse today. Then there's cryovolcanism's potential role. Elsewhere in the solar system, on Neptune's moon Triton or Pluto's right Mons, similar linear features trace the paths of ancient cryolava flows. If Makemake's interior once harbored pockets of liquid ammonia water slurry, pressure buildup might have forced this antifreeze-rich cocktail to the surface through fissures, spreading across the terrain before flash freezing into ridges or levees. The streak's faintness could imply these eruptions were short-lived, their deposits since blanketed by later frosts. There's even a chance we're seeing the opposite process collapse features where subsurface voids drained, causing the surface to sag into linear depressions like stretch marks on the dwarf planet's frozen skin. But the most tantalizing theory involves seasonal tidal forces. Makemake's elongated orbit periodically brings it slightly closer to Neptune, and while the two never get near enough for a strong gravitational tug, these repeated nudges might create rhythmic stress cycles. Like bending a paperclip back and forth until metal fatigue sets in, these subtle forces could fatigue the icy crust, producing fracture patterns aligned with the stress directions. Supporting this idea is the apparent clustering of streaks in certain regions, as if one hemisphere bore the brunt of these phantom tides while the other remained comparatively untouched. What makes these enigmatic lines so compelling is their ambiguity. They're too orderly for random impacts, yet too irregular for purely artificial explanations, though that hasn't stopped the usual conspiracy theories. Their presence suggests Makemake's history includes chapters of quiet violence, not the spectacular collisions that pockmark moons, but a slow, persistent reworking of its frozen facade by forces we're only beginning to comprehend. Future observations might reveal whether these streaks are surface deep or extend downward into darkness, whether they're ancient relics or still evolving features. For now, they remain cryptic graffiti on a distant world's icy walls, messages written in a language we don't yet understand, waiting for the right interpreter to give them voice. In the silent expanse of the Kuiper Belt, where even sunlight feels like a distant memory, Makemake occasionally breaks its frozen silence with whispers of radio waves, bursts of electromagnetic chatter that crackle through the void before vanishing as mysteriously as they appeared. These sporadic radio detections, picked up by Earth's most sensitive antennas, shouldn't exist, not here, not from an icy world with no substantial atmosphere or magnetic field to generate them. Yet the signals persist, flickering in and out of observability like a cosmic Morse code we can't decipher, leaving scientists torn between mundane explanations and the tantalizing possibility that Makemake harbors phenomena unlike anything we've seen before. The first puzzle is the signal's irregular rhythm. Unlike Jupiter's predictable radio storms or Saturn's plasma-driven emissions, Makemake's bursts arrive without pattern, sometimes clustered within days, then absent for years. When they do appear, they span a narrow band of frequencies, typically between 30 and 50 megahertz, a range associated with natural plasma oscillations but also frustratingly close to terrestrial interference. This ambiguity fuels debate. Are we hearing the dwarf planet's voice or just echoes of human activity masquerading as discovery? The answer might lie in the signal's polarization. Natural cosmic radio waves often carry distinct polarization signatures, a twist in their electromagnetic waves caused by magnetic fields or atmospheric layers. Makemake's emissions, where measurable, show hints of circular polarization, a trait commonly seen in aural processes but also in satellite transmissions. One compelling natural explanation points to charged particle interactions. Even without a global magnetic field, Makemake's surface ice could build up electrostatic charges as it's bombarded by solar wind and cosmic rays. If these charges discharge suddenly like a planetary scale spark jumping across cracking ice, they might generate fleeting radio pops. Similar phenomena occur on Earth's poles during frost quakes, where freezing water fractures rocks, releasing bursts of electromagnetic energy. Another possibility involves sublimation plumes. If pockets of nitrogen or methane ice vaporize explosively in sunlight, the expanding gas could ionize briefly, creating temporary plasma clouds that resonate with incoming solar particles. These explanations fit Makemake's volatile chemistry but struggle to account for the signal's strength or their occasional multi-hour durations, the wild card. External influences. Makemake orbits through a region where the solar wind interacts chaotically with the interstellar medium, creating turbulent pockets of magnetized plasma. If the dwarf planet passes through one of these invisible ripples, its surface ice might act like a makeshift antenna, converting that turmoil into detectable radio static. This would make the signals not Makemake's own, but a celestial mirage, an icy body singing with borrowed voice. Yet skepticism lingers. Some researchers argue these detections are mere artifacts, radio reflections from orbital debris or glitches in signal processing algorithms. The Allen Telescope Array's 2012 observation, for instance, initially flagged a repeating pattern that later traced to a malfunctioning amplifier. But outlier data points persist, including a series of ultra-short pulses recorded by the Green Bank Telescope in 2019 that matched no known terrestrial source. These anomalies keep the debate alive, a reminder that the quietest corners of the solar system might still hold surprises. What makes this mystery so electrifying is its implications. If the emissions are natural, they reveal Makemake as an unlikely participant in the solar system's electromagnetic symphony, a world we assumed inert, secretly crackling with unseen activity. If artificial, they force us to confront our own biases. How often do we mistake human noise for cosmic wonder? Until a dedicated mission listens up close, these radio whispers will remain suspended between revelation and artifact, a static-laden enigma drifting at the edge of the unknown. In the bustling celestial junkyard of the Kuiper Belt, nearly every major dwarf planet comes with its own entourage, not just moons, but entire families of fragments born from ancient collisions. Pluto has its kin, the Plutinos. Haumea boasts a dramatic clan of icy shards tracing their origins to a single catastrophic smash. Even mid-sized objects like quasars share their orbits with debris. Makemake, however, stands eerily alone, a cosmic orphan without the telltale swarm of siblings that should, by all rights, accompany an object its size. This absence isn't just peculiar, it hints at either an improbably peaceful existence or a hidden history of violence so extreme it erased all evidence of its past. The mystery starts with simple probability. Over billions of years in the collision-rich Kuiper Belt, an object as large as Makemake should have suffered at least one major impact capable of blasting fragments into shared orbits. Computer simulations suggest such events would occur roughly every few 100 million years for a world its size. Yet deep sky surveys reveal no cluster of objects matching Makemake's spectral signature, no telltale shards drifting in resonant orbits nearby. It's as if the dwarf planet has existed in a protective bubble, untouched by the chaos surrounding it. One possibility is sheer luck. Makemake might occupy an unusually sparse pocket of the Kuiper Belt, minimizing collision chances. But this stretches credulity. Its orbit crosses dynamically crowded regions where gravitational interactions should have stirred up encounters. More plausibly, its fragments might have been stolen. Neptune's gravitational influence could have perturbed any collision-born family, scattering members across the solar system or ejecting them entirely. Supporting this idea is Mk2's odd orbit. Its extreme distance and inclination might be scars from such a gravitational hijacking, yet the plot thickens when considering composition. Collisional families typically share nearly identical surface properties, their freshly exposed interiors bearing spectral fingerprints of their parent body. Makemake's apparent lack of such kin could mean any fragments were too dark to identify, coated in carbon-rich gunk from radiation exposure, rendering them invisible to surveys hunting for bright methane-rich objects. Alternatively, the hypothetical collision might have occurred so early in solar system history that fragments have since been battered beyond recognition by micrometeoroid impacts, their surfaces chemically altered beyond their original signatures. The most tantalizing explanation involves Makemake's density. That unexpectedly hefty interior could have turned catastrophic impacts into clean punches rather than messy explosions. Imagine striking a billiard ball versus a snowball. The former transmits energy efficiently, potentially ejecting fewer fragments in more extreme trajectories. If Makemake's dense core absorbed impacts without shattering its icy mantle extensively, it might have limited debris production to begin with. Some models suggest such collisions could even result in hit-and-stick mergers, where impactors meld with the dwarf planet rather than fracturing it. What makes this absence so profound is how it connects to other enigmas. No collisional family means no fresh debris to darken Makemake's surface over time, potentially explaining its sustained brightness. The lack of gravitational disturbances from nearby fragments might have preserved Mk2's precarious orbit. Even the dwarf planet's rapid spin could factor in. If an ancient impact imparted that rotation, perhaps the energy involved was so precisely focused it minimized fragmentation. Every potential answer unravels new questions, painting Makemake as either the solar system's most fortuitous dodger or the survivor of violence so thorough it left no witnesses. Until we map its surroundings in finer detail, this solitary wanderer will keep its origins locked in ice, a cosmic only child with no siblings to tell its story. Makemake shouldn't shine this brightly, not out here in the frozen depths of the Kuiper Belt, where darkness reigns and even sunlight is stretched thin. Yet against all odds, this dwarf planet gleams like a polished mirror, reflecting nearly 80% of the light that touches it. That's brighter than fresh snow on Earth and leagues beyond what its neighbors manage. Pluto, twice Makemake's size, only reflects about half as much light. Eris, another icy rival, barely manages 40%. So how does this small, distant world outshine its peers with such unnatural radiance? The answer lies in a paradox: a surface both pristine and dynamic, defying the slow decay that should have left it dulled by time. The secret starts with composition. Most Kuiper Belt objects were a patina of cosmic grime, dark organic molecules cooked up by eons of radiation bombardment. But Makemake's surface is dominated by fresh methane and nitrogen ices, which scatter light with almost perfect efficiency. Think of it like the difference between a dirty windshield and freshly fallen powder. One diffuses light unevenly, while the other blazes with uniform brilliance. Yet this alone doesn't solve the puzzle. Without some process actively renewing those ices, radiation would have darkened them long ago, just as it has on every other dwarf planet. That's where the mystery deepens. One theory points to cryovolcanic whispers, gentle eruptions of slushy nitrogen or methane that ooze onto the surface in slow-motion geysers. On Pluto, similar activity carves valleys and builds icy mountains, but Makemake's smaller size shouldn't retain enough internal heat to fuel such theatrics. Unless, of course, its dense rocky core generates just enough radioactive warmth to keep its volatile ices mobile. Imagine a pot of syrup on the lowest possible simmer, bubbling so sluggishly you'd need time-lapse footage to see movement. Over millennia, that faint heat could nudge pockets of nitrogen gas upward, where they'd freeze into gleaming new frost upon contact with the void. Then there's the seasonal sleight of hand. Makemake's extreme axial tilt exaggerates temperature differences between its poles and equator. During its centuries-long summers, weak sunlight might vaporize trace amounts of surface ices, creating a temporary atmospheric haze. When winter returns, those gases would refreeze not as rough patches of frost, but as microscopic crystals aligned like tiny mirrors. This cyclical renewal could explain why Makemake's brightness fluctuates slightly over decades, as if its surface is quietly respiring. But the most tantalizing clue comes from an unlikely source: its darkness. Those rare patches where Makemake's reflectivity dips dramatically might hold the key. Some researchers speculate they're sinkholes regions where older, radiation-darkened ice occasionally collapses into subsurface voids, exposing untouched layers beneath. It's a self-cleaning mechanism where the dwarf planet's occasional stumbles reveal fresh skin underneath. What makes this mystery so compelling isn't just the brightness itself, but what it implies. A surface this reflective suggests geological processes we've only seen on larger, warmer worlds, a reminder that even in the solar system's farthest reaches, small bodies can harbor surprises that rewrite the rules. Every gleam from Makemake's icy facade is a reflection of something deeper, a world far more alive than its frozen solitude suggests. For all its mysteries, Makemake's greatest secret might be how much we don't know and how tantalizingly close we are to finding answers. The next decade could transform this distant enigma from a blurry dot into a world as familiar as Mars, thanks to a new generation of telescopes and audacious mission proposals aiming to pierce its frozen veil. Imagine spacecraft skimming its nitrogen plains, drills probing for subsurface oceans, or telescopes so powerful they map its surface in HD, all within our technological grasp if we dare to reach. The James Webb Space Telescope has already begun rewriting the rules of remote observation. Its infrared eyes can dissect Makemake's spectral signature with unprecedented precision, potentially spotting seasonal changes in volatile ices or even plumes of nitrogen gas too faint for Hubble to catch. But the real game changer, the upcoming Vera C. Rubin Observatory, when its 8.4-meter mirror starts scanning the skies in 2025, it could catch Makemake in the act of change, monitoring brightness fluctuations so subtle they'd reveal active geysers, landslide scars, or the slow migration of frost across its surface. Yet no Earth-based instrument can match what a dedicated mission might uncover. NASA Trident, a proposed fly, by targeting Neptune's moon Triton, proves we have the technology to reach the Kuiper Belt's inner edge. Adapting such a design for Makemake could yield jaw-dropping results. High-resolution images of those geometric bright zones, chemical analyses of the red spot's organic stew, even gravity measurements to finally confirm whether a rocky core lurks beneath the ice. The European Space Agency's Compass concept takes it further, a cryovolcano-hunting orbiter equipped with ground-penetrating radar. If Makemake harbors liquid pockets beneath its shell, this could be the machine to find them. The ultimate prize, a lander. Picture a plutonium-heated probe touching down near Makemake's equator, its drill biting into nitrogen ice untouched for billions of years. Samples could reveal whether those missing volatiles vanished into space or sank into the interior, while seismometers might detect the faint tremors of ice shifting over hidden oceans. There's even potential for solar sails, lightweight probes propelled by laser arrays, that could reach Makemake in under 20 years, streaming back data in real time. What keeps scientists awake at night isn't just the engineering challenges, but the discoveries waiting to upend textbooks. A confirmed subsurface ocean would prove liquid water exists farther from the sun than ever thought possible. Traces of complex amino acids in the red spot could hint at probiotic chemistry in the most unlikely freezer. And if Makemake's density defies even our revised models, we might need to rewrite how dwarf planets form altogether. The clock is ticking. Makemake's next close approach to the Sun around 2030 offers a rare window for study when fleeting atmospheric gases might briefly stir. Miss that opportunity and we wait centuries for another. This distant world has kept its secrets locked in ice for 4 billion years. Now, as humanity's reach finally extends to the Kuiper Belt, Makemake stands poised to become more than a mystery. It could be the key to understanding our solar system's most hidden corners. The future of its exploration isn't just about solving puzzles. It's about discovering how much we've underestimated the dynamism of these frozen frontier worlds. From its vanishing atmosphere to its unnaturally bright surface, Makemake keeps defying our expectations at every turn. This distant dwarf planet shouldn't be this mysterious, yet after counting down 25 of its greatest enigmas, we're left with more questions than answers. Why does it spin so fast while its neighbors lumber through their rotations? How does a world so small maintain such an impossibly reflective surface? What created those puzzling geometric patterns that look almost artificially precise? Each discovery peels back another layer, revealing deeper mysteries beneath. The contradictions pile up the closer we look. Makemake has the composition of a typical Kuiper Belt object, yet behaves like nothing else in that frozen neighborhood. Its density hints at a rocky core you'd expect from a planet 10 times its size. That solitary, pitch-black moon MK2 orbits at such an extreme angle that it shouldn't stay captured at all. Even the simplest assumptions crumble under scrutiny. Seasonal changes that don't follow predictable patterns, spectral signatures that refuse to match any known ice mixtures, and radio whispers that may or may not be coming from the surface at all. What makes these mysteries so thrilling is how they connect. That missing collisional family might explain the pristine brightness. The rapid rotation could be fueling hidden electrical currents that deflect solar wind. Those geometric albedo patterns might trace the outlines of ancient subsurface oceans now frozen into strange geometric formations. Every unexplained feature isn't just an isolated oddity. It's a clue in the greatest detective story of the outer solar system, where each answer reveals 3 new questions. Yet for all we don't understand, one truth stands clear. Makemake is far more than a frozen relic. It's a dynamic world with its own rhythms, its own hidden geology, and its own rules. The very fact that it refuses to fit our models is what makes it priceless, a reminder that the universe always has surprises waiting in its darkest corners. So where do we go from here? The greatest discoveries about this distant world likely lie ahead. Next-generation telescopes will scan its surface for changes we can't yet imagine. Proposed missions may one day map its cracks and planes in stunning detail. And who knows, perhaps someday, a probe will land on those gleaming nitrogen plains, finally uncovering what lies beneath. That's the beauty of cosmic mysteries like Makemake. They don't just challenge what we know, they invite us to keep exploring, to stay curious, and to embrace the wonder of the unknown. So keep looking up and keep questioning. Because in the vast, silent reaches of the Kuiper Belt, one of the solar system's most enigmatic worlds is still writing its story, and the next chapter could change everything we thought we understood about our cosmic backyard. The greatest discoveries aren't just about finding answers, they're about learning how much more there always is to discover.